So I want to introduce today a totally new type of number for you guys. So these are some types of numbers that you're already familiar with. You probably learned about them in roughly this order in your math career as well. Our focus today is imaginary numbers. So as is often the case, imaginary numbers came into being because somebody was trying to solve a particular problem, ran into sort of a roadblock, and decided to invent a new mathematical idea to get around it. So here is the issue that we're trying to solve here. So it says find zeros of this particular function. That means, of course, that I want an x such that f of x is equal to 0. So I want to solve this equation. And you will already see right away that we can't factor this, right? Because there's no two numbers that multiply to 1 and add up to 0. Because the two numbers that multiply to 1 must have the same sign, right? And no two numbers with the same sign are going to add up to 0. So we can't factor this. We'll try the only other tool in our toolkit. We're going to say x is equal to negative b plus or minus the square root b squared minus 4 times a times c all over 2a. So I just did quadratic formula, right, with a equals 1. B is 0, right, because there's no second term. And then c is 1. And as we simplify this, you probably see the problem already. So underneath the square root, I get negative 4 over 2. And you probably were taught by a previous math teacher to write no solution in this case. Or if you had a really good previous math teacher, you were probably taught to write no real solution. We're going to graduate beyond this now. The reason we would say no real solution in the past is because the solution here is what is called an imaginary number. So an imaginary number is a number we're going to invent to solve this particular type of problem. Let's make our problem a little bit more specific first. So if we have a graph of this function, you can graph it on your calculator if you want, or you can just notice that this is just a plain old x squared parabola shifted up by 1 unit. So my graph is going to look roughly something like this, right? The reason now we can't find any zeros should be pretty obvious based on our work in previous lessons. Our zeros are our x-intercepts, and this graph has no x-intercepts. So it never touches the x-axis. Okay, so what these numbers are for is representing these zeros. So the zeros are functions that never touch the x-axis. Now you may think that this could not possibly be useful in real life. It's literally called imaginary as opposed to real. That's certainly what I thought when I was in your shoes. However, if you study music at all, or you make beats on your computer, you may be familiar with sound being made up of waves, right? So this is what you get on your computer if you plunk the C key on a piano and let your computer listen. And this is very clearly, obviously, a really complex function. It has all these peaks and valleys, and is really difficult to write down in such a way that a computer can understand it. Hundreds of years after these imaginary numbers were first introduced, somebody discovered that imaginary numbers were a really easy way to write down these functions in such a way that your computer can interpret them. So anytime your computer is dealing with sound, anytime you play even like a song on YouTube, your computer is using imaginary numbers to unpack those sound files. If you study signals in college or electrical engineering, this idea is going to come back up. Unfortunately, it's a little too hard for us to tackle. You can tell by the way it looks, a little too hard for us to tackle in this class. For now, we're just going to concern ourselves with just the basic moves of dealing with these imaginary numbers. So by definition, we're going to let I represent now the square root of negative 1. And then the implication of that is I squared must be negative. So this is the only number squared that gives you a negative number. That fact is really all we need to evaluate these complex numbers, these imaginary numbers now. So the square root of negative 64, I'm going to give you this example and I'll let you tackle a couple on your own. The square root of negative 64 is really 64 times negative 1. Square root of 64 is 8 times square root of negative 1. And this really is, if I is the square root of negative 1, 8i. So that's how we write this down in terms of that number I. I'm going to give you the solutions to these next two in just a second here, after you've tried them on your own. So here are those solutions step by step. And notice now, when I have I in two different terms, so these come from obviously my negative square roots, I can combine them just like as if it were 3x plus 4x, right? So like terms still apply. So that's super convenient and satisfying, is that these numbers follow the same rules as we're used to, right? And you've even actually done this kind of breaking down of square roots before to simplify them, and earlier in your math career as well. We're going to use the fact that we can treat these numbers sort of like x's to tackle this problem over here. So this is the product of two complex numbers, and I can actually use a Punnett square to multiply them together, just as the same as if they were x's. And then negative I times 3i is negative 3i squared. Okay, let me write that out, and then this actually has an interesting result. So negative 3i squared, and then I combine like terms for 13i, and then plus 10. Remember, I squared now is negative 1, so I'm going to plug that in for I squared. Okay, and notice I actually get a real number when I square I. So positive 3, and then I can combine that with my 10. So we have this thing that somebody literally made up to tackle these imaginary solutions, and it turns out it ends up following most of the same rules as all the rest of our numbers do, which is pretty satisfying. Our main idea here before we move on is that these guys show up when we look for roots of functions with no x-intercepts, right? And they behave similarly to real numbers, except for, we'll say I squared equals negative 1. So that's the only number whose square is negative. Okay, once you have the notes, we're going to tackle some examples of quadratic formula with these negative square roots. All right. So I am going to do actually the second one, and then I'm going to let you do the first one on your own, because the first one is a little bit easier. So I'm going to let A be 9, B be negative 6, and C be 2. And then I'm going to solve using quadratic formula. Okay, so I've plugged everything in. You should, by the way, pretty much have the formula memorized at this point in your math career. If not, you have notes on it in a previous lesson, right? And then I'm going to simplify. So I get a negative 36 underneath the square root. Make sure if you're squaring this negative 6 in your calculator, you're putting that in parentheses. Now, here's where that imaginary number I comes in. So I get 6 plus or minus the square root of negative 36 is 6i, right? Because the square root of 36 is 6. The square root of negative 1 is I, all over 18. And then I'm going to simplify. So I'm going to divide both terms by 18, and I get 1/3 plus or minus 1/3 I. So the way I want to write the solution down in this case is it's really 2 points, right? 1/3 plus 1/3 I and 1/3 minus 1/3 I. I apologize for not giving you enough room here. So those are my solutions to this equation. This quadratic equal to 0. Try the top one now on your own, and I'll give you the solution here in a second. So you should have gotten to this point, 10 plus or minus 4i over 2, because we got a negative 16 in the square root. And then I'm going to simplify negative 5 plus minus 2i when I divide both terms by 2. And that is really the two solutions, negative 5 plus 2i, and then negative 5 minus 2i. Okay, so that is the solution there. So the steps here, it's really the same as quadratic formula has always been, except for you no longer stop if you get that negative. And then we should notice a pattern here. In our solutions, plus, minus, and then 1/3 plus 1i, or 1/3 I, 1/3 minus 1/3 I. So the solutions always
follow this pattern here, that they're the same except for the sign in the middle, and that's because of the plus minus that you're already familiar with in that quadratic formula. These are called conjugate pairs, which is vocabulary you're going to see later in your math career. So conjugate pairs. That is also the main idea here, that these solutions occur in conjugate pairs with this result I. So that is a helpful pattern to pay attention to as you begin to practice these.